Well, thank you very much. Actually, I did not come here to teach, but to learn. I will try to prove that with my talk, that I have a lot to learn. For example, how my own thing here works. Okay, so I'm going to talk about, oh, there's the big stick. Yes, I remember that. Oh no, but I will use the laser pointer. Yeah. So I will talk about joint work with various co-authors. Pablo Castaneda, who is now in Mexico, was at IMPA at the time. Juliette Hell from my group. Brian Smith from the group of Klaus Ecker, who is more in differential geometry. Carlos Rocha at Lisbon. And then contributions by other people who I will mention as we go on. So first, let me talk about meanders, the way or the part which I know least about. I will start with the part which I know least about, and then I will later talk about differential equations and how I got into all these meander troubles where I'm looking for your algebraic combinatorial help and all kinds of topics. So what is a meander? I'm starting with parentheses, open, close parentheses, open, close, and because I never know which parentheses matches which one, I draw an arc for the opening, closing match, okay? So here's an example. Now, I can also do this below the horizontal line and match parentheses, and these parentheses, since they are all nested, I call a rainbow. This is slightly different from the notion of rainbow that Piotr Zograf used in his talk. Now, I can combine these. I can have an upper set of open-close parentheses, a lower set, and look what kind of a diagram happens. And if this diagram is a single Jordan curve, like in this example, I call it a meander, more precisely a closed meander. Okay, fine. So pairs of parentheses, but sometimes they close, sometimes they don't close. And how to count them, what the asymptotics are, all these things are very unclear to me. Okay. Poincaré stumbled on those, I should have mentioned, in 1912 when he was thinking about twist maps of an annulus, what we now call twist maps. Area preserving maps in an annulus in the plane where you rotate the inner circle to the right and the outer to the left should have at least two fixed points, the Poincaré-Birkhoff fixed point theorem. He kind of proved this, but then Birkhoff completed the proof later. Unfortunately, Birkhoff discarded with the meanders, and so they were forgotten for a long time. But we are excavating. So I want to relate first the meander to billiards. Here is the poor man's billiards. This is like on a checkerboard, a grid, on an integer grid. I put the corners on integer coordinates in the Cartesian grids, and I start at a half integer on the boundary, and I shoot at 45-degree angle, and then I reflect minus 45 degrees and so on. And I want to convince you that this is the same as the meander down here, because if I take these points here along the horizontal line and I enumerate them on the boundary here, then you see, for example, that this point A, where I start with the upper arch, goes to the 1, 2, 3rd next point on the circumference. So I close this horizontal line to become the boundary of my billiard, and there's a one-to-one correspondence between the two. If I choose the right shape of the billiard, okay? So this does not work. Of course, the reflection thing here depends on the shape of the billiard, and the shape has to be chosen smartly enough that these meanders correspond to the billiard in that shape. And it's not a rational billiard. I only take half integer values. I don't take rational angles. I only take angle 45 degrees and so on. So it's very, very special. On the right, you see a matching of parentheses above and below the horizontal line, which are not connected, you know, are not a Jordan curve. So there is this little sausage here, which corresponds to this little rectangle. So the billiard may be transitive or not transitive, corresponding to the connectivity of the curve here, or non-connectivity. And I will try to convince you that I know so little topology that I do not even understand Jordan curves in the plane. So there are questions about these Jordan curves in the plane. Okay? Another connection is to Temperley-Lieb algebras, which I know even less about than billiards, so let me get done with that quickly. But if you want to talk to experts, there is a book here of Lando Zvonkin, and there is a book of a former student of mine, Anna Karnauhova, who has related meanders to all kinds of things like global attractors, seaweed algebras, Young-Baxter equations, beta-ansatz, and so on. Aha. And here we are. So a Temperley-Lieb algebra, think of this as an algebra of matrices with a weird multiplication rule. The multiplication rule, is that you take the square of a generator. Here they are n+1 generators. E0 is a trivial one, and EI squared is factor tau in the Lie algebra, distinguished element times EI. The commutator vanishes if I and j are at distance 2 or more, and there's a funny rule here with the nearest neighbors, okay? And you can graphically denote that. That's how the relation to the meanders comes about, by writing E1 as this little rectangle thing here. You draw these two little humps or pimples and two straight lines. With E2 you draw the pimples a little bit below and the straight lines, and with E3 you draw the pimples here. Now, what has this got to do with the meander I showed you? Well, let us do a trace operation. Let us calculate the trace of this product. The product is simply that you put these diagrams next to each other, and the multiplication rule is that when you put these things next to each other and you do isotopies, if you see a little isola somewhere in here, then you replace it by a factor tau, if an island appears. You see, because EI squared, I mean, then if I draw this diagram twice, I would have a little island here. That's the tau which comes out in front. So that's all you need to know about how to do calculations in this Hopf algebra. Now, the trace is defined by taking the right and the left end and joining them at equal heights outside the diagram. So in other words, if I take the right and left piece of this diagram, E2, E1, E3, and I spread it out to become a horizontal line, I see this upper diagram, and the lower rainbow denotes the trace operation. So that there is a way to relate the meander diagrams and their connectivity to the fact, true or not, depending on the product, that the trace of this Lie algebra element is, of this Hopf algebra element is tau. Okay, so this is another formulation. Now,
sorry, is this algebra finely dimensional? Is this algebra finely dimensional yet?
Yes, yes. This is. It has the multiplicative generators E1 to En. I mean, it's finitely generated. Okay, finely generated, and you can represent it by matrices. Okay. Now, let me do a few examples. So this diagram is supposed to indicate a nested sequence, a rainbow of P open-close pairs. So I have these P open-close pairs, and I take Q open-close pairs here. And on the bottom, to match this, I have to take P plus Q, of course. Now, this configuration is a meander if and only if the numbers P and Q are coprime, do not have a common factor. You can think of this as, in the billiard, as a P times Q billiard, like a rectangle. And if you do play billiard in a square, it is very easy because every point goes ping, pong, pong, boom, and comes out exactly where it started and reflects as if the square had never been there. So you can contract all the square and you get a Euclidean algorithm. And in the 1 by 1 square, ping, pong, pong, boom, of course you have a closed curve, right? Inside the 1 times 1 square. So that's the proof of this fact. Now, if you have P, Q, and R nests, it's a little more difficult. You have to take the least common the greatest common divisor of P plus Q and R plus Q. And if you take P, Q, R, S, I do not know a simple formula. I do not know. I thought it should be, you know, there should be a formula in terms of P, Q, R, S, and you do this and that. And Stefan Liebscher and Anna Karnauhova have designed a kind of rather complicated, somewhat Euclidean-looking algorithm which reduces the question of is this thing connected or not to smaller and smaller cases, and finally to one of the known cases. But I mean, we don't have a formula, okay? So anybody is welcome to.
It's called Razi induction.
It's called?
Razi induction.
Razi induction.
Yeah, I can.
It's known.
Sorry?
This is a known thing.
Yes.
Very good. That's why I want to talk to you, okay? And if I have T, if I have 5 and so on, this is known for all?
Well, for any number, there is a fast algorithm to test whether it's
logarithmic of logarithmic complexity.
Well.
Because that's the point, logarithmic complexity, right? Linear complexity is trivial. You go ching, 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 ching.
Well, I can show you some examples.
Very good. Okay, yeah. So let's talk more. So already I'm succeeding to learn. Thank you very much. So this is a part I know nothing about. And now comes the part where I tell you how I stumbled on all these questions. And this has to do with differential equations. So one of the cheapest, simplest partial differential equations is the following. I have a function of variables t and x, and I take the heat equation and maybe a nonlinearity, which depends on x, u, and the gradient of u. This is on the unit interval. And maybe to make people happy, I take Neumann boundary conditions for x equals 0, 1. So these are called Neumann boundary conditions. Now, if this is still too complicated scalar equation, I don't want to assume much on f. It is interesting that this equation perhaps has variational structure. So there is a gradient functional which ensures that any bounded solution of this in appropriate spaces converges to equilibrium, equilibrium being a solution u which is independent of time. So solutions, of course, are supposed to depend on t and x. Now for ordinary differential equations, I copy this equation, I just put u equals 0, u sub t equals 0, and I have fxv, dxv, and maybe 0 equals dxv. And again, I copy this is from 0 to 1, and I have a boundary value problem for an ordinary differential equation, second order ordinary differential equation. So I call v of x equilibrium solution. Time-independent solutions of the partial differential equations. But if I look at the equation, I can also call it a pendulum. Okay? This is a pendulum equation. If I forget mean, if I forget that I wanted to do partial differential equation and I say acceleration is a force, then this is a pendulum equation. It's a funny pendulum, a general pendulum. It could be van der Pol oscillator. It doesn't have to be a mechanical pendulum. Okay. So let me talk about pendulum meanders for a while. So Jim York and others have, a long time ago, have seen that these pendula can have chaotic motions. For example, if the nonlinearity is periodic in X, doesn't even have to depend on V sub X. So area preserving case, here I think you have friction and excitation, and you get very complicated motions if you wait long with the time X. Huh? I mean, what was space is time now, okay? Sorry for the pendulum, but okay. So if you have a very long interval, that corresponds to very long time, and the spatial dynamics, the complexities you encounter when you look just for equilibrium solutions of your nonlinear heat equation are reflecting the chaoticity of what other people would call the pendulum. Okay, so I'm trying to brainwash a little bit to see the time of the pendulum as actually the space in a partial differential equation. Now, let's see what happens. Let us solve this boundary value problem. What do numerical people do to solve such a boundary value problem, for example? They say, okay, in the V sub X plane, I'm looking for equilibria. I'm with this ODE case. I solve the boundary condition at, so X goes to the front, V goes to the right, V prime, the velocity, V sub X goes to the top. We start with Vx equals 0, that's just the V axis. We have solved the boundary condition at X equals 0, wonderful. Let us propagate forward by just solving the differential equation, and this horizontal line will start winding around. It will become a surface in this three-dimensional space, and it will be, well, more or less right winding, because if Vx is positive, V increases, and if Vx is negative, V has to decrease. So I have a positive winding here, and here is an example surface. It may look like, the surface may look like that. Now I intersect that surface, which I get from the line of initial conditions, with the horizontal line again, which is the boundary condition at X equals 1, and I get all the solutions of my equation, all the equilibrium solutions of the partial differential equation, all the solutions of the boundary value problem. This is called the shooting method. Okay? So if I look at these intersection points and their trajectories going backwards, they come from somewhere here and wind around on the surface, these form a braid. It's a positively winding braid in 3 dimensions. Okay, and we see a meander here in front. Look, here in front is our meander of the type which we saw before, almost. Fusco-Rocha came up with this description of solutions for the pendulum, and we already mentioned Poincaré, who encountered such diagrams, and Arnold introduced them. Oh, there's a difference to the previous situation, because before we had a closed meander with our parentheses, you know, there was an arc from here to here, but we can make this an open meander by just taking the rightmost top arc, which you would call a rainbow, and flip it over to the left, and we have precisely the sort of diagram that we get in ordinary differential equations. But this was for the ordinary differential equation, not for the partial differential equation. So now we have seen how the meander somehow appears in a rather concrete way when we study the equilibrium configuration, the time-independent configuration of a dynamical system, which actually depends on time. So what do the solutions here do? Well, the solutions here don't do much. They can be equilibria, for example, V1, and here's another one, V2, and they can go from one equilibrium to the other in infinite time, of course. That's all that a solution which is defined for all real time can do. So these solutions is what the global attractor consists of. So this was a concept, all roads lead to St. Petersburg, okay? I apologize for that, by Olga Larizhenskaya in 72. In the context of Navier-Stokes equation, this equation is much easier. And so here are these two equilibria and the heteroclinic orbit. And in our setting, the global attractor, the set of all bounded solutions, the set of all sometimes called eternal solutions from negative infinity to plus infinity in time. They define a set which attracts any bounded set of initial conditions. So you start with a bounded set of U0 in an infinite dimensional space, and it gets smaller and contracts onto something, and that object, that limiting object, is the global attractor. And in our case, it consists of points and arrows between them. Points and arrows between them. It's like a combinatorial object. It's like a graph. Who connects to who? There cannot be cycles in this connectivity because we have a functional going down all the time for the partial differential equation. So there's a variational aspect here. And on the other side, we have the pendulum ordinary differential equation, and we have Poincaré, Arnold, what have you. And we have, for example, orderings of our equilibria. We can enumerate them, we can order them at the boundary x equals 0, x equals 1. The orders may be different, and they define a permutation which measures how the equilibria are ordered differently at x equals 0 and at x equals 1. In other words, how this surface was winding around when we followed the pendulum equation. So how do these two things correspond to each other? Well, if we know the global attractor, we know all equilibria, we know these things, we know the meander, we know everything. But can we go in the other direction? Suppose we only have equilibrium information. Do we know what the global attractor is going to look like? Let us check. So here's what I was talking about. I am talking about equilibria, which are sitting on this surface. This is the x-axis, this is the v-axis, and we get different orders of these equilibria at the right and on the left and on the right. And you see how in 3 space I indicated this. These spaghetti are winding around each other. I call this the equilibrium spaghetti to avoid the word braid. Okay. Now here is the permutation I was talking about, because I can number the equilibria along the I messed this up, yeah, along this axis or along that axis, and the discrepancy is reflected in this ordering. Okay, no, it's correct. So 1A347, 1A347. If I number the intersections along the meanderic curve, 1, 2, 3, 4, 5, and the shooting surface determines the permutation, but also vice versa. Okay, so the braid type is, in this case, because it's a positive braid, it is determined by this permutation. A positive braid sitting on a surface. Why Sturm? Very briefly. I call all this business Sturm because there is a Sturm-Liouville type structure behind that, which Sturm actually discovered in 1836. If you take any two solutions, U1, U2, of the same PDE, non-linear, Sturm was thinking linear, okay, non-linear, and you take the difference of them, then the difference satisfies, I call it W, satisfies a linear non-autonomous equation. And that, if that difference has a double zero somewhere, I'm plotting a profile at time t0 in x, has a double zero here, then before it had to have 2 zeros and afterwards none. So PDE people know about comparison theorems. This is a much more refined version of comparison theorems. Comparison theorem says if you start above, you stay above. That would be the case, z equals 0. Now the consequences, and I will not go through the details, this is just a survey, the consequences of this are enormous. Among other things, they let us go from this meander diagram to the global attractor, the Ladijenskaya PDE object, which in our case depends on the equilibria and their unstable manifolds, the guys which are going to an equilibrium in backwards time. These are finite dimensional manifolds. Their dimension is the Morse index of this thing as a critical point in the functional, which is lying behind here. So this is basically the setting. And this works as follows. So these were theorems from the 1990s until approximately 2000, joint work with Carlos Rocha. A permutation for a meander arises from a pendulum if and only if it is a meander. Well, it cannot intersect itself by uniqueness of initial value problems of ODEs. If it is a meander, if it is Morse, that is a positive winding condition. So this restricts, not all meanders are allowed here, but we know exactly which ones in a simple combinatorial condition, and are dissipative. Dissipative means they fix the first and the last entry. This is simply because in a dissipative system, you have a topmost equilibrium and you have a bottommost equilibrium. And these correspond to the first and the last point in our meandric curve. Moreover, the permutation defines all heteroclinic orbits. Who connects to who? So this combinatorial object, this permutation, tells us from the ODE, from the ordinary differential equation, tells us the partial differential equation information, who connects to who and who doesn't. And determines means it's really easy. You can write a computer program which does that. It's even easier. Namely, even I can write a computer program which determines that, okay? And I did. And the next theorem says, if the permutations are the same, then the attractors are the same. They are C0 conjugate. This is another type of rigidity, if you like. The discrete information already tells you, up to homeomorphic continuous classes, what the attractor looks like. Okay? So this is how we go from permutations to the PDE, and then you can do numbers and calculate. It's a very old slide. How many permutations, how many meander permutations are there? How many of them satisfy this positive winding condition, which I mentioned? Approximately half of them. Then you can mod out certain trivial symmetries, and you can count global attractors. Now on the left, these columns have of course been studied have been studied here. And here are, as an example, all global attractors which can happen in this Sturm class, with up to 9 equilibria. With equal 9 equilibria. So here all of them. They are 18 and some of them look really the same. And if you restrict the nonlinearities, F, to depend only on U, so you don't allow X and you don't allow dxu, so this is the integrable Hamiltonian case, then many of these disappear and it simply cannot happen. So, in terms of our Temperley-Lieb algebra, if we took this product and opened the rightmost loop, so that we get a meander of open meander type that we need in the pendulum, then we get this particular global attractor. So now I associate geometric objects like cell complexes to each of these meanders. And the question is, can I go in the other direction? Let me give an example. So here is the Snoopy Attractor. So I want to go, we have gone from ODE meander to complexes, and now we want to go in the opposite direction. And here's an example. This is a disk which has three faces, two-dimensionally unstable equilibria in the centers, three attracting equilibria, and I call this the Snoopy Attractor because it looks like, you know, the two eyes and the snout and the ears and so on. So can you have Snoopy as a sandwich in this attractor business? In other words, can I have, what is a sandwich? A sandwich consists of an upper part and a lower part, which is three-dimensional, so it's a half ball, if you like, a three-dimensional ball topologically, and in between is the meat, I mean, in between is the Snoopy, okay? Is it possible to realize that in this class of Sturm, in this class I'm talking about, yes or no? Well, the answer is not the whole sandwich. That is not possible, does not occur in this class. But if you just take a bun, like half the sandwich, you know, just the bottom part, and you put Snoopy on top, that occurs in the class. So there are rules, you know, the design is not so clear, and I want to have some sort of a Lego. I want to have cell complexes, look at them, and figure out, do they occur in this class? And if yes, what is the permutation, or don't they? And the stupid way to do this is to write all meanders and to enumerate everything, and then look whether what I want to have is in that list. No, I want to see this directly. So, from complexes to meanders. So, figures are by Anna Karnauhova. So, let me talk for a moment about this object, about this global attractor. I said this consists of unstable manifolds. Now, even in calculus of variations, the boundary of an unstable manifold of an equilibrium may be a very complicated object. It need not be a manifold. However, here we have a Schoenflies theorem, which says that the boundary is a sphere. So that our global attractor is what topologists call a regular cell complex. That's a cell complex, like you have the cells and you have these attaching maps, but the attaching maps are actually homeomorphisms. It's not like you lump together some part of the boundary and squeeze it. Now the boundary here, I said, are really spheres. They are not length spaces or anything complicated. Still there's a question how all this attaches to each other. Moreover, there are hemisphere decompositions. There is a plus-minus structure here, which is even finer than just attaching spheres to each other. When you look at an unstable manifold of an equilibrium, of dimension n, inside there is a faster unstable manifold. These are the guys who leave that equilibrium faster, of dimension n minus 1, and an even faster of n minus 2, and so on. This is what Arnold calls mustaches. You know, I mean, I'm sorry, I cannot demonstrate, okay? But if you have a mustache which goes like this and goes like that, then let's see. This is the fast guys, okay, and the slow guys go out like this until a fast component takes over. So this decomposes, for example, a two-sphere boundary of a three-dimensional unstable manifold into an upper or lower hemisphere, or I chose an eastern and a western hemisphere, okay? Because you can make jokes about east and west this way. Here, so we classified these structures geometrically. This is more or less 10 years of work. We got up to 3 balls. This is how stupid we are. Okay, so if you have a single 3-cell, a single 3-dimensionally unstable equilibrium, and on the surface of that is invariant, the boundary, that's a 2-sphere, and you decompose that into faces, 2-dimensionally unstable manifold, into edges, 1-dimensionally unstable manifold, into vertices, stable equilibria, then these are all possibilities with 13 equilibria. Okay, out of 13 equilibria, approximately 400 or 500 attractors which occur here. And we find these systematically, and here are the meanders for the associated equilibrium spaghetti. I'm not telling you exactly how we do this, okay? Here's another example with 15 equilibria. That's the solid tetrahedron. Well, the tetrahedron has only 4 corners, but I have to add the corners and the faces and the edges and the center thing because it's a solid tetrahedron. Here is a here's the 4-dimensional tetrahedron. And if you think in terms of meanders, except that they are open, so I have shifted top and bottom, you see a rainbow on one side, and on the other side you see nests, and it's 1, 2, 4, 8. So if you take the powers of 2 on the one side and the rainbow on the other, you get the simplices. It's a little exercise, not completely trivial, to even see that this is a Jordan curve always, okay? Just on the way home on the tram, okay? For the hypercube, you have to do something different. There are other realizations of the hypercube, but one possibility is to take 1, 3, 9, 27, so the powers of 3, okay? And you also take the powers of 3, but in the other direction. That gives you the hypercubes as an example. If you want to do octahedra, disaster strikes. So I thought octahedron, so you have this 4-sided pyramid and also below, like a double cone construction over the square. And I thought, yes, so I take the antipodes, this top of the pyramid and the bottom of its mirror image down there. And this will be the top equilibrium in my global attractor and the lowest one in the global attractor. Remember, we had a highest and lowest equilibrium in the ordering of that attractor. I call this highest and lowest equilibrium the north and the south pole for obvious reasons, you know. I mean, the highest one and the lowest one. That did not work. I mean, I went about this originally really stupidly. I said the ordering on the left and on the right boundary are Hamiltonian paths, which visit each vertex once in this graph, where each face has a face center, each edge has an edge center, and they go from north to south, okay? And then I have to study pairs of those and check the meanders, and then I go back from these. If I have meanders, then I can go back and construct the attractor and see whether it's the octahedron. Okay, so this is how I let the computer check it. There were approximately 110,000 or so Hamiltonian paths from north to south if they were adjacent on the octahedron, and maybe 90 or 95,000 when they were opposite. And in the opposite case, in the diametrically opposite case, not a single attractor resulted. And this is due to rules how these complexes have to be glued together. And I did not give you those rules in detail, okay? Because it's just a colloquium talk, and it's you know, it's getting late. But with neighboring north and south poles, there are 4 octahedra. I also said that I decompose the ball into an upper and a lower hemisphere, or a western and an eastern hemisphere. How this is becoming popular these days, again, for unknowable reasons. Now, one of the hemispheres here consists of only 1 triangle out of the 8 triangles on the octahedron, and the other is 7 triangles. There are 4 possibilities, 4 meanders which arise from that decomposition. If I decompose into 2 plus 6 faces, then there is a single meander which realizes that, and 3 plus 3 doesn't happen. 3 plus 3, 3 plus 5, 3 plus 5 doesn't happen, and 4 plus 4 doesn't happen either, okay? It's not realizable. So these are all the 3-dimensional octahedra, and then I developed a crazy obsession. I wanted to do the 4-dimensional octahedron, which on the surface has 16 tetrahedra, and they are somehow glued together. And I ended up with this. This took me about 2 months to construct, because that doesn't seem to be a rule, or at least not a rule I understand. It's not like with the simplices, you know, 2, 4, 8, 16, and chuck, you have them all, or the hypercube. So I try to convince you that there are lots and lots of examples, and I have no clue how this all fits together. Not to speak of the understanding the relation to the meanders. Okay, this is why I want to talk to the meander gurus. Black holes. Oh yeah, we have a little bit of time. So, different, seemingly completely different topic. Everybody's interested in black holes, so there are certain solutions of the Einstein equations, and and then if there are several of them, maybe they send out gravitational waves. You know how this so this gravitational wave business is also interesting, right? I mean, they have run on the order of millions of simulations of colliding black holes and such things. And then they solved Einstein equations, and they found certain characteristics what these waves should look like. And now they measure something, so they measure lengths in various places of the Earth, and extremely accurately, and then they get signals. And then they look in the database. And if the signal matches anything in the database, they announce, we have discovered such and so. Namely, we have discovered the simulation, what the simulation was for. I think this is a rather problematic approach. I asked them, how many fake data sets do you have in your database, for example? Because they should discover in the database, and afterwards they should be told whether it was a fake data set or not, just to test the statistics. I mean, I think there are some problems okay, but anyway, we are much more modest. We look at a single black hole, and we look at, we are sitting out here, and to be safe from physics, I want to know what's going on inside the black hole. Okay? So I want to solve the Einstein equations where we cannot look. For example, is it rotationally symmetric inside or not, or what? So we make an ansatz as to the metric inside, and we leave some freedom in one variable, that's the stuff which is going outside, and then we have a metric on the standard metric on the two-sphere, and And before we can start solving the Einstein equations, we have to solve something called Einstein Constraints. And I have no clue, but I'm sure you could explain to us what these Einstein Constraints really mean. I asked them to give me partial differential equations which formulate these Einstein Constraints, which initial conditions for simulations of the Einstein equations would have to satisfy in order to be consistent. So, if I scale these become a parabolic equation. The Einstein equations themselves are hyperbolic due to Minkowski metric, but we get a parabolic equation for the Einstein constraints, which with a degeneracy, so it looks like a nonlinear or heat equation. And we tried to look at that, and we found actually bifurcations. We found objects which satisfy Einstein constraints but are not rotationally symmetric. And the deviation from rotational symmetry, depending on a parameter which we can put in our equations, this is like a prescribed curvature equation. We get these various isotropy types which I indicate here. So this allows us to construct new non-symmetric Einstein initial data inside the black hole, and then hopefully someday we'll put them in a computer program and tell us what the resulting dynamics is from that. Now, a student of mine, Filippo Lapisi, who is now in Brazil and in Lisbon and so on, he said, yes, but in all of your cases, there is a symmetry breaking where you still keep a rotational symmetry of your solution. And so that the solution really depends only on this time variable t, which corresponds to this radius here upwards, and theta, which is one of these angles here. We have the two-sphere, so we rotate around an axis and we get one remaining angle. And what do we see? We see an equation of this Sturm type. So that's why he is carrying over now the whole theory which I presented in a semilinear setting to nonlinear settings, and then the heteroclinic orbits that we found mean certain initial conditions for this black hole dynamics. So that is his work. So he can talk about Sturm global attractors, Sturm permutations, and meanders, and so on, as they appear in this problem of general relativity. Yeah, in the last couple minutes of my talk, I want to say a few words about the meander history. So I already said that Poincaré, aiming for a completely different thing, stumbled on meanders, and but there are earlier examples. Gauss, for example, studied 1840 curves which are intersecting themselves, if you like, on the two-sphere. And then he defined Gauss words, namely he marked the crossing points, in this case 1 and 2, and a Gauss word would be 1, 1, 2, 2. So the question was, once the intersection points are marked, in which order are they traversed by the curve itself? So which orders are possible? And he actually went diligently to, there was no TV, there was no internet. I mean, what could these people do? They would write tables of meanders which occur, right? And he marked certain words which would not appear. So these were called Gauss words later, and I think the combinatorics of a number of Gauss words as intersection goes to infinity is also not known, or it's still not known, right? So this is this setting, and of course in our meander business. So maybe if we do something like this, we only have to close up artificially at the ends here, and then we will say that we have a Gauss word A, B, C, D, E, F, G, where first these intersections occur one after the other, A, B, C, A to G, and then, horizontally, and then in some other order. And this other order is precisely the meander permutation which we were discussing. So what we are doing here is a special case of these Gauss words. Now this is an older example. I'm not sure you can we switch off the light or somewhere, or because yes, yeah. This is from the Cathedral of Chartres, and so this is around 1200. And you have a floor pattern, which if you open it up, clearly shows you a meandric pattern. So these patterns are older than Gauss, even older than old Gauss. Here is a page from a book which illustrates Theseus. See, I can never guess American pronunciation of Greek words. Can you say it in Greek? Huh? No, in Greek. In Greek. Theseus, okay. So this is the authoritative pronunciation. And the Minotaur, which looks like a cute little dog here. And it's a very similar sort of labyrinth which we can unfold or open up to be a meandric pattern. Now this thing is much older. This is something I saw when, when you live in a city like Berlin, there are museums, and the first 10 years I lived there, I didn't go to any museum. But of course, the first time I go to St. Petersburg, I go to Hermitage and so on. So this is a clay tablet in the which I saw in the Pergamon Museum. Don't go, it's going to be closed for another 5 years or so for renovation. And what you see is these patterns here, right? Of meandric type. Now, I took a picture, so I took this picture, and I thought, wow, wonderful. This clay tablet, oh, I forgot to say from when this is. This is about 1800 before Christ, of Babylonian origin. So this is older than Chartres and so on. What was this good for? This was good to foretell the future. So much for applications. Okay, this would be an industrial application. Predict the future. Huh? So what they did, so this was for students. This was for students of divinity who did divinations, who threw intestines of sheep on an altar. I was on the verge of going somewhere and actually looking at intestines of sheep just to see how this was done. So I think you have a sheep and 30 meters intestines or something, and you throw these on the altar, and then you make it planar probably a little bit, and you obtain a pattern like this. And then from this pattern you are supposed to tell what is going to happen. And a student of mine, who I mentioned this in class, and the student said, oh, can I see these pictures? And he said, oh, but the instructions are written on it. Here, this is a little bit destroyed. These are cuneiforms. So this is text which explains what that pattern is supposed to mean, and how there is a palace and the winds and what's going to happen to the king and so on. And then I talked to an expert. Well, I shouldn't tell that. Okay, I talked to an expert, a colleague of mine, a very fine lady. She explained to me the background. So around 1800, there was a revolution in Babylonian science, if you like, or they tried to make this more scientific, because these oracles were very unreliable. Specifically, she told me that the outcome and the reliability of the oracle would depend on whether or not the neighbor had slept with his wife in an appropriate, or let us say inappropriate way. She was very detailed on these practices. And so depending on that, the outcome of the oracle would be spoiled and so on. So it came out of fashion around this time to use this elaborate canon, which students had to learn what these meanders mean. And of course, I would love to see more of these clay tablets. They have one in Berlin, okay? They have one of these. And presumably there are boxes of those somewhere in the dust of Iraq, if they haven't been destroyed yet. Except we don't have the rights to translate. I had this brilliant idea before the Iraq War to send a student there and have him look at these clay. No, we cannot access them because we don't get the rights to translate. They can read that. You know, of course we can read. I mean, if the text is not destroyed, okay? But I would love to see a systematics of how far they got with the classification of meanders in Babylonian times, for whatever, like to reverse engineer from the predictions how systematically, how they went about this, how systematically they went about these things. But the change was that they went to astronomy. So the origin of astrology as a prediction of the future, which paid for Kepler. I mean, Kepler's job was to tell the emperor's horoscope of next year. not of this year, of next year, because the emperor had to decide whether to wage and prepare and wage war next year, not this year. Okay, so it's the same kind of origin. So to rely on horoscopes, that change, which she identifies as an origin of science, perhaps, or the scientific method, if you like, comes from that time to do away with the unreliabilities of the neighbors' predilections. Now here's a somewhat older emblem, which is not really a meander, but an elaborate spiraling diagram. And this is a bracelet which has been radiocarbon dated to be about 15,000 years old. So we see that meanders are a very old story. Now, as a summary, we have not predicted the future. We have just studied how partial differential equations give rise to ODE meanders, and then we attempted, and we were, so far we are partially successful, this is an ongoing project, how to go from signed Thom-Smale complexes, complexes which are defined by the dynamics in a variational setting, cell complexes, how to determine these Hamiltonian paths from north to south, which we then can identify with a meander, and from that meander we can in turn classify the resulting attractor, and we want to do this in such a way that the diagram closes up. And this is as far as we got to 3-ball, okay? So not general three-dimensional complexes yet, but we are working on it. And here is a list of the topics I mentioned, and maybe we can have light again, and I will be delighted to listen to your questions and remarks. Thank you for your attention.
Any questions?
Not about the future, please. Yes, please.
So, yeah, so we consider meanders corresponding to tetrahedron, octahedron, and so on, but there are some exceptional regular polyhedron like dodecahedron. Okay, I can spell this, but
Icosahedron. I brought some. Now, okay, so there's, yes, but please ask your question first.
so yeah, about other meanders corresponding to other exceptional regular.
So he's asking, is that all you can do? Now, one little theorem or corollary, one little corollary to what I said is the following. Take a three-dimensional cell, a 3-ball, on the surface, put any regular cell complex, any planar, well, planar except for this thing at infinity, okay? Regular cell complex. Then there exists a realization in this class. Exists means that we single out one of the cells to be the Western Hemisphere, and all the other cells, no political description intended, and all the other cells belong to the Eastern Hemisphere, okay, all together. And then you still have to orient, have to give orientation to the edges, and the orientations of the edges are, I didn't really describe the entire process, but are essentially a bipolar graph. A bipolar graph is one which you can hang up at one point, and then it only goes downhill and no cycles and so on. Okay, so we find some realization for any of these guys, but as I said, with the octahedron, the three-dimensional octahedron. In this case, if I start with one triangle as the Western Hemisphere, the North and the South Pole has to sit on the shared boundary between the Western and Eastern Hemisphere. So this points to what is going on in the Arctic, right? So they have to be in particular adjacent. Okay, they cannot be diametrically opposite. To describe all possibilities is another issue. But I have, in preparation for your question, I have brought not the dodecahedron, but if I can find this, the icosahedron. I have to first. I'm not even sure whether this works. You don't see anything. One second, please. So here is the icosahedron in a somewhat unusual presentation, okay? But perhaps you see the triangle here, and here is a triangle, and there's a triangle. And then the back of this whole thing is also a triangle, okay? So this is the presentation which we use. And we use a 3D icosahedron, and I think the maximal pole distance in this case is actually 1, and the maximal decomposition into, so the Western Hemisphere can have at most 2 faces, and it does. Here the Eastern and Western Hemisphere are separated by the green north to south meridian, so maybe this goes through Greenwich, and this is the date line, and this is everything, all the rest, and then we have something out here. And what is the meander? The meander looks like this. But you see the icosahedron, I mean, this is not part of a family which goes to arbitrarily high dimensions. But in principle, of course, I want to study all these polytopes and what have you, and associate meanders to them. But not yet, okay.
So to any polyhedron, you have at least one meander, right?
3-dimensional, yes. Yes, 3-dimensional, yes. You see, so the most recent state of affairs is the following. If you give me any regular cell complex with hemisphere decompositions like I described, you have Western, Eastern Hemisphere of any dimension, of course, now. And so that you have like plus and minus signs there. Then I can take this guess and I can associate in a unique way 2 Hamiltonian paths through all the edges, through all the vertices, Hamiltonian paths, which then I can interpret as a permutation, and then I can start drawing. But the resulting curve may not be a meander. I am lacking the the requisite geometric conditions on signed hemisphere decompositions, which would only give meanders. But if it comes from Sturm, then I know what I must do, and then I can only hope for the best. And I'm convinced that if the associated thing is a meander with this little positivity condition, so that it has an associated global attractor, that then the cell complex, the signed cell complex of that global attractor will coincide with the cell complex I started with. Okay, but there are more gaps than bridges at the moment. Okay, and all the bridges are drawn up, or this, so it's really complicated.
Any more questions? If not, then let's thank the speaker again.
Well, thank you. Thank you for your time.